Hello, Rouse. Let's talk about logarithmic functions. When logarithmic functions are introduced, usually in the textbook and maybe even sometimes in the lesson, they are introduced as the inverse of exponential functions. So consider, say, like a common logarithm like this. We would have been able to write it as y equals log base 10 of x. And then we could write that in exponential form and say, oh, okay, well then, since a logarithm is an exponent, this means that y is the exponent that I place on a base of 10 to receive the power x. So I have an exponent, a base, and a power. And then I could always invert and get that y is equal to 10 to the exponent x. And that's the inverse right there, f inverse. So I imagine a base exponential function growing by a factor of 10. And I'm relatively familiar with this type of function. It's going through 0, 1, 1, 10, negative 1, 1/10. It has a horizontal asymptote of y equals 0. Has an unrestricted domain, a range where y is greater than 0. It's always increasing. Its rates of change are also exponential. And everything was fine, I suppose. And then, right, to sketch the original, well, I guess I would just then invert that inverse. And here's the line y equals x, and I reflect across that line, and okay, now I get an idea of what the logarithmic function looks like. We don't want to have to do that every single time. Okay, we should, I mean, I'm not going to erase it because all of this is fine, but sometimes as soon as students see a logarithm, they write it in exponential form, and that's an inefficient approach, let's say. Okay, well, let's try to develop an understanding that this function is its own function without worrying about an inverse. Okay, where we have a base of 10 and our inputs are going to be powers. If we want nice integer values, then we would choose powers of 10, but we don't need to choose powers of 10. And our outputs are logarithms. Outputs are logarithms, and logarithms are exponents, not powers. Right? We need to know the difference between an exponent and a power. So try very, very hard to be able to reason through this. Okay, notice my skewing of my scale a little bit, because I know that any power of 10 is going to be positive, that there's no power of 10 that I can use that'll give me a negative number. And then I can create a table of values, I suppose, in my head, where I'm thinking about, oh, what power do I want to receive and what exponent do I need to receive that exponent. There you go. Guess that's why there. So like powers of 10 that I'm familiar with include 10 and say 100. If I go backwards, I notice that 1 can be written as a power of 10 and 1/10 can be written as a power of 10. 10 is the first power of 10, 100 is the second power of 10, 1 is the 0th power of 10, and 1/10 is the negative 1th power of 10. Right. In other words, to receive a power of 1, I use an exponent of 0. Here's my power of 10. Here's my exponent that I place on a base of 10. So 1, 0. To receive a power 10, I use the exponent 1. To receive the power 100, I use the exponent 2, so I'm heading towards 100, 2. To receive the power 1/10, I use the exponent negative 1. To receive the power 1/100th, I use the exponent negative 2. To receive the power 1/1000th, I use the exponent negative 3. And I discover a vertical asymptote. Right. Yeah, let's move that point up to there, I suppose, because we're not going to be doing square grids very often. Should be a bit of a smoother curve like that. Okay, there's f without thinking about it as being the inverse of something else. Right? F has a domain where my powers of 10 are any real number that is greater than or equal to 0, or sorry, greater than 0. My range, though, exponents that I can place on a base of 10, there's no restriction there, is there? So this is me discussing my powers. This is me discussing my exponents. If I focus on my use of language there, I should develop an understanding. I have a vertical asymptote of x equals 0. That's because my power will never be 0. There is no power of 10 that is equal to 0. that causes a discontinuity. I guess I see the behavior that if my power gets closer to 0, then my exponent needs to decrease without bound, and that's what causes the vertical asymptote. Okay, and behaviors as my powers grow, my exponents will have to grow. They do not grow very quickly. In fact, they grow slower and slower and slower, but they will get larger and larger. The fact that they grow slower and slower is caused by the fact that my rates of change are actually approaching 0 from values that are greater than 0. Okay, my rate of change here is positive, and this curve gets shallower and shallower and shallower. It does this without a horizontal asymptote. This is just, this shouldn't be too much of a surprise for us, because if we think again temporarily about the inverse here, this curve's outputs went up forever, and it went right forever. This curve right here is going to go right forever and up forever. It can't have a horizontal asymptote. If it had a horizontal asymptote, that would mean that there would be some largest exponent that I was allowed to place on a base of 10. And that's just not true. The left-hand end behavior, as x approaches 0 from values that are greater than 0, as my powers approach 0 from powers that are greater than 0, my exponents are going to decrease without bound. The rate of change here increases without bound. So it's very, very steep in that direction. Okay. Let's try it with another base exponential function. Try it fresh. Let's say we draw a sketch of g of x, or just do a full analysis of g of x equals log base 1/2 of x. So I know that powers of 1/2 have to be positive. So I'm not going to waste any space with the second or third quadrant. And I am going to say, to receive a power of 1, I use an exponent of 0. To receive a power of 1/2, I use an exponent of 1. To receive a power of 1/4 from a base of 1/2, I use an exponent of 2. To receive a power of 1/8 from a base of 1/2, I use an exponent of 3. So it's my understanding of these terms that what I'm graphing here are exponents that I place on a base of 1/2, and that these right here are powers of 1/2. Okay, no calculators required, no inversion is required, writing in an exponential form is not required. It comes from an understanding of the terms that we're talking about. To receive a power of 2 from a base of 1/2, I would need an exponent of -1, wouldn't I? To receive a power of 4, I could use an exponent of -2. To receive a power of 8, I could use an exponent of -3. Here, let's analyze one of these, or a couple of these ordered pairs here. Let's look at 2, -1. 2, -1 is an element of G because we'll have a couple of different reasons here. Well, G of 2 is going to be log base 1/2 of 2, which is going to be the exponent we place on a base of 1/2 to receive the power 2. I don't want to have to write down. Okay, so G of 2 is going to be, let's see, 2 to the exponent. G of 2 is going to equal 1/2, and I guess that means that 2 to the exponent G of 2 is going to be 2 to the exponent -1. Therefore, G of 2 is equal to -1. Okay, I should be able to solve exponential equations, but I should be able to do a lot of this in my head here. We draw a curve. That looks like this, and hopefully eventually we'll be able to just draw, oh, this is a decay logarithmic curve versus this is a growth logarithmic curve, in the same way that I'm probably not doing a full table of values to draw y equals 10 to the exponent x. Like that. Its domain is the same as above, its range is the same as above. In the same way that exponential functions all have the same domain and range before they're transformed. Range exponents can be any number at all. Vertical asymptote is still the same, x equals 0. X-intercept is still the same, didn't mention that before. The x-intercept is 1, and that's because if I want to receive a power of 1 from any non-neutral base, from any positive base, the exponent that I use is going to be 0. That's why these logarithmic curves originally pass through 1, 0. And behaviors best read from the sketch. As x grows without bound, y decreases without bound. When my powers get, when my powers get larger, in this case, my exponents have to get smaller. The rate at which they get smaller is approaching 0. These rates are all negative, so my rate of change is approaching 0 from rates that are smaller than 0. To the left, as x decreases towards 0 from values that are greater than 0, as my powers get closer to 0 from powers that are greater than 0, my exponents are going to have to get larger on this base that's less than 1. And the rate at which my exponents change is growing very quickly. Let's get that labeled. And there we go. All right, try to think of them as their own functions. Try to do a table of values in your head. Read domain and range should make sense from the equation if you understand the terms. Make sure that you're using the terms base, power, and exponent appropriately, and practice it by trying it out.